Okay, so now this is kind of getting closer to understanding what we mean by positive and negative charge. But what about, where does this electric field come from? How do we, where do we start from? What's the fundamental basic thing here? Well, we start with the force law, really. The force between two charges, and the magnitudes of those charges are Q1 and Q2. It's just the product of those two charges times K, which is a constant of nature, 8.987 times 10 to the 9th Newton meters squared per Coulomb squared. Just to get us into newtons over here, if we use coulombs and meters and so forth, R is the distance between the two charges, and we square it, as it turns out. So the product of the charges divided by the distance squared times this constant would give us the force. Now, as I said, we could, if we knew the angle of those two threads with respect to each other and the masses of those balls, calculate the force between these two charged up little aluminum covered balls, which are very light, but they're pushing each other apart because there's a certain amount of positive charge on each one that we transferred there. And you can see that even though gravity is pulling them together, the electric force is pushing them apart. Now, the force is always along the line separating the two charges. If you draw a line in between the two charges, that's the direction of the force. If by convention, if F is positive, we have a repulsive force, as we see there. And if we have F negative, that's an attractive force. Now we can demonstrate attractive forces too. And we can do it using this rod, which is amber. We're going to rub it with wool. Turns out if you rub amber with wool, you get negative charges. So those two balls are positively charged, right? If I put the amber rod there, it attracts them. It actually neutralized the charge on there. Okay? So now the balls are, again, sticking together. They're not attracted to each other. Gravity is just knocking them down. Now, suppose I put even more negative charge on them. What's going to happen if I transfer negative charge to them? Now they're both negatively charged. And they're still pushing each other apart. Why? Well, look at our force formula, right? What does the force formula say? Because Q1 and Q2 are both negative in this case, negative times negative is positive, positive force is repulsive. So even though they're negatively charged, we still get a repulsive force. Now how can we demonstrate an attractive force? We can do that with this empty aluminum can. Now aluminum is a metal, right? And the main thing that characterizes metals is that charge can flow around freely. Now, we remember that Ben Franklin got it wrong. We probably should have called electrons positively charged and protons negatively charged. That would have been a little bit easier to understand. Why? Because what are we actually doing here? When we put positive charge on this, we're not putting an excess of positive charges. We're stripping the electrons out of the atom. We know electrons are negative, and we pull a bunch of electrons off this way. So now that's leaving these bare protons here without electrons shielding them. So there's a net positive charge here. So now this is positively charged, and I'm going to put it near this can. What's going to happen? It's going to draw the electrons in the can toward it. So the electrons are moving, and the electrons want to jump and be by those positive charges. And I can move the can without even touching it with this rod. It's almost like magic. But that's just because this rod is charged up. Now I can prove that to you. I'm not just cheating or blowing on the can or anything. I can ground this rod, get rid of all the excess positive charges on it. This This thing is attached to a wire. The wire goes into, ultimately, the third pin on the wall plug there. The third pin on the wall plug goes to the ground wire in the building, which goes to a rod pounded into the ground somewhere, okay? Ground really means ground, into the earth itself. Earth is pretty conductive because of the water and so forth in it. Now this should have very little charge on it, and you can see it has almost no effect, a lot less effect on the can as it did before. All right, so we got rid of I tried to get rid of the charge. It's kind of hard to do, actually. Now what will happen, just think about it for a second. So the positively charged rod was drawing the electrons close to it, right? And the electrons wanted to be by that positive rod, and they were dragging the can along with it. What if we do that with the negative? Right? So whoops, not with amber. Amber, you use the wool. I don't know why. Just magic. We do our magic trick again. So now this thing is negatively charged. I put it near the can, it's going to push away the electrons, right? Because they have the same charge. Like charges repel. So now when I put wait, what's going on? Well, it pushes away, it pushes the electrons to the other side, leaving bare positive charge, which is attracted to this rod because it's negatively charged, right? So it doesn't matter, no matter, with this experiment, no matter what you do, it's an attractive force. So you can't get away from that. Now, if this is negatively charged, what did I have on those there? Negative or positive charge? It was still negative charge, right? So I can put a little bit more negative charge on these guys. I have to be very careful here. Hey. Yeah, okay. Now they have plenty of negative charge. Let's try to neutralize that with, where's my amber rod? Or not amber rod, glass rod. Try to neutralize that by just putting a bit of positive charge on it. No, I didn't put enough on. I didn't touch it well enough. Come on, you guys. Maybe I put too much charge. Trying to neutralize these is hard. So let's ground them, get rid of all the charge on them, and see what happens. Yep, now the two little aluminum covered balls are just hanging there in space. This thread gets twisted up a bit, but they're not anymore charged up. Let's unwind that. And you can see that there's no tendency for them to push apart. Because these are metal on the surface, if they were charged and they touch each other, if one was positively charged and one was negatively charged, what would happen? When they touch each other, it would neutralize itself. So you can tell the fact that they're touching means that just gravity is pulling them down. They have zero net charge on them.